Hello everyone. Welcome to the fifth or the final part of the introduction to Verilog lesson series. In previous lesson, we looked at modules in Verilog in detail, and in this lesson, we look at gate level modeling in Verilog. Now, this will be helpful when you specify the module internals in gate level. Actually, in this CO221 course, you will be modeling circuits only with gate level modeling in Verilog. The content covered in this lesson is related to the chapter 5 in the reference book. So if you want to get more information, you can read the chapter 5 of Verilog HDL reference book. First, we'll look at how basic logic gates are supported by Verilog. Now, Verilog supports basic logic gates as predefined primitives or inbuilt modules. Now, these primitive logic gate modules can be instantiated just like you instantiate a usual module in Verilog. And as you might already have realized, since these gate modules are predefined by Verilog, you don't need to define these modules yourself in order to use them in your design. Here you can see the basic gates supported by Verilog and the module names of these predefined primitive gate modules. The gates and O, NAND, NO, etc. are supported by Verilog by default. Here you can see a few examples on how you can instantiate basic gates in Verilog. The output wire connected to each gate here is named out. The input wires, the two input wires connected to gates are named in 1 and in 2. And first you can see how basic instantiations work with two input gates such as AND, NAND, etc. So you need to first connect the output wire and then the two input wires. Each instantiated gate is given a unique name as well, as you can see here. Next, you can see how you can connect more than two inputs to a gate. The example is about a 3-input NAND gate actually, and still you need to connect the output first. That is common to all the types of gate instantiations. The output wire should be connected first, and then you should connect all the inputs. Here in 1, in 2, in 3 are connected after the output wire out. And finally, you can see something which is valid only for instantiation of gate modules in Verilog. And you can see we have instantiated an AND gate module without a unique name given to it. But this is a legal and valid gate module instantiation in Verilog. This is because giving a unique name is not compulsory when you instantiate a gate module. But again, you should remember that this is valid only for instantiation of predefined gate modules in Verilog. This is not valid for other modules that you define in Verilog. Now here's a quick recap of what we just saw. First, the instance name does not need to be specified for primitives. That is, it's not compulsory to give a name for the instantiated gate modules. And this actually lets the designer instantiate hundreds of gates without giving each of them a separate unique name. Also, more than two inputs can be specified in a gate instantiation. And gates with more than two inputs are instantiated by simply adding more input ports in the gate instantiation. Here, this is about another new technique or a syntax you can use in Verilog. This syntax you can use when you want to instantiate an array of instances. That is a set of similar instances. Here in this example, we have got the need of instantiating 8 NAND gates. And each of these gates should have 2 single bit inputs and 1 single bit output. So for this, we have defined 3 buses or multiple bit wires. First, we have defined 3 8-bit wires actually, named as out, in 1 and in 2. Now we want to create 8 NAND gates and connect inputs and outputs properly. The main idea here is to create 8 NAND gates using a compact syntax. Here, after we want to create 8 NAND gates and connect the 0th bit of in 1 and 0th bit of in 2 as inputs to the 0th NAND gate, and then connect 0th bit of the output via out as the output of 0th NAND gate. And then we want to do this with other bits in the multiple bit wires we defined earlier, so that respective bits in wires are connected to a separate NAND gate. So finally we need to have 8 NAND gates to which these inputs and outputs are properly connected. So this you can do easily with one line of code as given in the example. So you first use the NAND keyword and then a name for the array of gates. Since we are going to define an array of NAND gates, we are giving a name for this whole array of NAND gates, and we have the given name here is the, n underscore gate, and then you need to specify the size of gate array. We have specified it as 7 to 0, so that 8 gates indexed from 0 to 7 are instantiated. We then should connect the multiple bit wires to the gates array, so that respective bits of each of these multiple bit wires are connected to the respective gates. So if it was not very clear, and to understand this better, an expanded version of this line of code we wrote earlier is given next actually. So the code line we wrote is totally equivalent to the collection of given 8 instantiations of NAND gates named from N gate 0 to N gate 7. So in a compact way, we instantiated all these 8 NAND gates by using the syntax we discussed. Okay, so now with this we are actually done with all what you need to know about gate level modeling. So it's not very difficult, and there are no big concepts here. And actually the next thing you should do is to do some examples so that you can verify whether you understood all the concepts that we discussed so far. So starting from here, you are given 2 example designs that you can try modeling with Verilog. So this first example, it's about modeling a gate level multiplexer. So you all have looked at multiplexers in digital design course, and a multiplexer basically is a circuit that chooses among multiple inputs and forwards a chosen input to the output. So the selection is done based on the selection inputs. In this example, S0 and S1. So here is a 4 to 1 multiplexer that chooses between 4 inputs I0, I1, I2, I3 based on the selection input lines S0 and S1. So the high level block diagram with the function table, uh, they have been given in the slide. Now we need to model this multiplexer using gate level modeling in Verilog. So this is an exercise for you to try out. Anyway, in this slide, you are given the gate level design of the 4 to 1 multiplexer to make your life easy actually. Anyway, I hope you all know how to get to this gate level design using the knowledge you have gained in the 2 to 1 course. By the way, we have given you the gate level design so that it's easy to get started. So now your task is to model this circuit using gate level modeling in Verilog. Also, you should try to write a test bench for this 4 to 1 multiplexer so that you can verify whether it works as you expect. Because at any time, like when we are done with designing or modeling a particular circuit element with Verilog, the next immediate thing that we should do is writing a test bench to see or to verify whether it works as we expect. So you can do the same here for the gate level multiplex as well. So try this on your own and let me know if you get into any issues. And this is the second example that I want you all to try out. It's a 4-bit adder that you need to model using Verilog. Now actually in a previous lesson we saw an example code for this 4-bit adder. But there, if you can remember, the 1-bit full adder, it had been written using behavioral modeling in Verilog. And then it was used to build up the 4-bit adder. Here, in this case, you should write the 1-bit full adder using gate level modeling and use it multiple times in a higher level module to get the 4-bit full adder. So that is your task. And here you can see how you should connect 4 1-bit full adders to get the 4-bit adder we want. So to make your life easier, we have given that as well to you. By the way, this design actually we saw in one of the previous lessons as well. You have to write a module for this one as well. In total for this example, you will have to write 2 modules, one for the 1-bit full adder and then a higher level module for the 4-bit full adder that instantiates 4 1-bit full adders in it. And finally, you will need to write another module. So you should know by now what is the next module that you need to write. That is the test bench module. So you need to write a test bench module to verify the functionality of the adder. And you can try this one as well on your own and let me know if you get into any issues. So actually this is all about Verilog concepts that I wanted to cover, and you will be given a lab task to do with Verilog, which will be counted as the 8th lab for the course or the last lab for the course. And I will post the lab sheet on Fields and let you all know. So if you have any issues or doubts regarding what we covered regarding Verilog HDL, you can use the discussion forum available on the Fields course page to get them clarified. And also we'll try to arrange an online session to discuss the issues you might be having. So that's all, and thank you all. Goodbye.